Hello and welcome. In this video, we will explore two key applications of mathematical induction, a fundamental proof technique in the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to use induction to prove statements about divisibility and to prove inequalities. These are powerful tools for proving statements that hold for all natural numbers or for all integers greater than a certain value. Let's begin with our first objective, proving divisibility using induction. This is a common type of problem in number theory. The core idea is that if an expression is divisible by an integer d, we can write it as a times d, where a is some other integer. This is the definition of divisibility. Let's work through a classic example. We want to prove that the expression f of n equals 7 to the power of n minus 1 is divisible by 6 for all natural numbers n. So, our proposition, P of n, is that 7 to the n minus 1 is divisible by 6. Remember, the principle of mathematical induction has two main steps, the base case and the inductive step. Step 1 is the base case. We need to show that the statement is true for the first value of n. In this problem, n belongs to the set of natural numbers, which we'll take to be 1, 2, 3. So we test the statement for n equals 1. We substitute n equals 1 into our expression, f of 1 equals 7 to the power of 1 minus 1, which simplifies to 6. Since 6 is clearly divisible by 6, our base case holds true. The statement is valid for n equals 1. Now for the second step, the inductive step. This is where we make an assumption and then prove a consequence. First, we assume that the statement is true for some arbitrary natural number k. This is called the inductive hypothesis. So we assume that 7 to the k minus 1 is divisible by 6. Using our definition of divisibility, this means we can write 7 to the k minus 1 as 6 times a for some integer a. Our goal is to prove that the statement is also true for the next integer, k plus 1. That is, we need to show that p of k plus 1 is true. We need to prove that 7 to the power of k plus 1 minus 1 is divisible by 6. In other words, we need to show it can be written as 6 times b for some integer b. Let's start with the expression for n equals k plus 1 and manipulate it using our inductive hypothesis. We begin with the left-hand side of our goal, 7 to the k plus 1 minus 1. Using the rules of exponents, we can rewrite 7 to the k plus 1 as 7 times 7 to the k. Now, we need to bring in our assumption. From our inductive hypothesis, we know that 7 to the k minus 1 equals 6a. This means we can express 7 to the k as 6a plus 1. Let's substitute this expression for 7 to the k into our equation. We get 7 times the quantity 6a plus 1 minus 1. Expanding this, we have 42a plus 7 minus 1, which simplifies to 42a plus 6. Finally, we can factor out a 6 from this expression, giving us 6 times the quantity 7a plus 1. Since a is an integer, 7a plus 1 is also an integer. Let's call this integer b. So, we have shown that 7 to the k plus 1 minus 1 can be written as 6 times b. This means it is divisible by 6. We have now completed both steps of the induction. We proved the base case, p of 1, is true. And we proved the inductive step, if p of k is true, then p of k plus 1 is also true. Therefore, by the principle of mathematical induction, the statement is true for all natural numbers n. We have successfully proven that 7 to the n minus 1 is divisible by 6 for all n in the set of natural numbers. Let's try another example, this time involving a product. We want to prove that n times the quantity n squared plus 5 is divisible by 6 for all integers n greater than or equal to 1. Our proposition P of n is that n times n squared plus 5 is divisible by 6. First, the base case. We test for n equals 1. Substituting n equals 1, we get 1 times 1 squared plus 5, which is 6. Since 6 is divisible by 6, the base case holds. Now for the inductive step. We assume p of k is true. Our hypothesis is that k times k squared plus 5 is divisible by 6. This means k cubed plus 5k equals 6a for some integer a. Our goal is to prove p of k plus 1 is true. That is, we need to show that the expression for n equals k plus 1 is divisible by 6. We need to prove that k plus 1 times the quantity k plus 1 squared plus 5 is divisible by 6. Let's expand the expression for n equals k plus 1. We have k plus 1 times the quantity k squared plus 2k plus 1 plus 5. This simplifies to k plus 1 times k squared plus 2k plus 6. Expanding this product gives us k cubed plus 2k squared plus 6k plus k squared plus 2k plus 6. Combining like terms, we get k cubed plus 3k squared plus 8k plus 6. Now, we need to use our inductive hypothesis, which states that k cubed plus 5k equals 6a. Let's rearrange our expression to find a k cubed plus 5k term. We can rewrite our expression as k cubed plus 5k plus 3k squared plus 3k plus 6. Now we can substitute 6a for the term in the parentheses. This gives us 6a plus 3k squared plus 3k plus 6. We can factor out a 3 from the remaining terms, giving us 6a plus 3 times k squared plus k plus 2. For this entire expression to be divisible by 6, the term 3 times k squared plus k plus 2 must be divisible by 3 and by 2. It's already divisible by 3, so we just need to show it's divisible by 2. We can factor k squared plus k as k times k plus 1. The product of any two consecutive integers, k and k plus 1, is always an even number. Therefore, k squared plus k is even. Since k squared plus k is even, and 2 is even, their sum is also even. This means k squared plus k plus 2 is divisible by 2. So, the term 3 times k squared plus k plus 2 is divisible by 3 and by 2, which means it's divisible by 6. We can write it as 6c for some integer c. Substituting this back, our expression becomes 6a plus 6c, which is 6 times the quantity a plus c. This is clearly divisible by 6. We have shown that if the statement is true for k, it is also true for k plus 1. Combined with our base case, this proves the statement by induction. Now, let's move on to our second objective, proving inequalities using induction. This is a more advanced application of the technique. The process is similar, but the algebra can be more challenging. The key is to use the inductive hypothesis to create a new inequality that helps you reach your goal. Consider the inequality 2 to the n is greater than 6n plus 1. If we test the first few values of n, we find it's not true for n equals 1, 2, 3, or 4. For example, at n equals 4, 2 to the 4 is 16, and 6 times 4 plus 1 is 25. 16 is not greater than 25. However, at n equals 5, 2 to the 5 is 32, and 6 times 5 plus 1 is 31. Here, 32 is greater than 31. The inequality holds. This means our base case for the induction must be n equals 5. Induction doesn't always have to start at 1. Let's formalize the proof. Our proposition, p of n, is that 2 to the n is greater than 6 n plus 1 for all integers n greater than or equal to 5. We've already established the base case. For n equals 5, 32 is greater than 31, so p of 5 is true. Now for the inductive step. We assume p of k is true for some integer k greater than or equal to 5. Our inductive hypothesis is that 2 to the k is greater than 6k plus 1. Our goal is to prove p of k plus 1 is true. That is, we need to show that 2 to the k plus 1 is greater than 6 times the quantity k plus 1 plus 1. This simplifies to showing that 2 to the k plus 1 is greater than 6k plus 7. Let's start with the left-hand side of our goal, 2 to the k plus 1, and use our hypothesis to work towards the right-hand side. We can write 2 to the k plus 1 as 2 times 2 to the k. From our inductive hypothesis, we know that 2 to the k is greater than 6k plus 1. If we multiply both sides of this inequality by 2, we get a new, valid inequality. So 2 times 2 to the k is greater than 2 times the quantity 6k plus 1, which simplifies to 12k plus 2. We've shown that 2 to the k plus 1 is greater than 12k plus 2, but our goal is to show it's greater than 6k plus 7. We need to prove that 12k plus 2 is itself greater than 6k plus 7. Let's consider the difference between these two expressions. We want to show that 12k plus 2 minus the quantity 6k plus 7 is positive. The difference is 6k minus 5. Since we assumed k is greater than or equal to 5, 6k must be greater than or equal to 30. Therefore, 6k minus 5 must be greater than or equal to 25, which is positive. This confirms that 12k plus 2 is indeed greater than 6k plus 7. Now we can chain our inequalities together. We have 2 to the k plus 1 is greater than 12k plus 2, which is greater than 6k plus 7. This means 2 to the k plus 1 is greater than 6k plus 7, which is exactly what we needed to prove. We have shown that if the inequality holds for k, it also holds for k plus 1. Combined with our base case, this proves the inequality by induction. Let's recap what we've learned. We've seen how to apply mathematical induction to two different types of problems. For divisibility proofs, the key is to use the inductive hypothesis to substitute an expression that contains the divisor. For inequality proofs, the key is to manipulate the inequality from the hypothesis to create a new inequality that helps you reach your goal. You are now able to use induction to prove statements about divisibility and to prove inequalities. These are essential skills for the IB DHL curriculum. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video and try them on your own before watching the solutions. Question 1. Prove that 5 to the n minus 1 is divisible by 4 for all natural numbers n. Question 2. Prove that 7 to the n minus 3 to the n is divisible by 4 for all natural numbers n. Question 3. Prove that n cubed minus n is divisible by 6 for all integers n greater than or equal to 1. Question 4. Prove that 3 to the power of 2n plus 2 minus 8n minus 9 is divisible by 64 for all positive integers n. Question 5. Prove that 2 to the n is greater than n squared for all integers n greater than or equal to 5. Welcome back. Let's go through the solutions together. For question 1, we need to prove that 5 to the n minus 1 is divisible by 4. The base case for n equals 1 gives 4, which is divisible by 4. We assume 5 to the k minus 1 equals 4a. Then we write 5 to the k plus 1 minus 1 as 5 times 5 to the k minus 1. Substituting 5 to the k equals 4a plus 1, we get 5 times 4a plus 1 minus 1, which simplifies to 20a plus 4, or 4 times 5a plus 1. This is divisible by 4. For question 2, we prove that 7 to the n minus 3 to the n is divisible by 4. The base case for n equals 1 gives 4, which is divisible by 4. We assume 7 to the k minus 3 to the k equals 4a. Then we write 7 to the k plus 1 minus 3 to the k plus 1 as 7 times 7 to the k minus 3 times 3 to the k. Substituting 7 to the k equals 4a plus 3 to the k, we get 7 times 4a plus 3 to the k minus 3 times 3 to the k. This simplifies to 28a plus 7 times 3 to the k minus 3 times 3 to the k, which is 28a plus 4 times 3 to the k, or 4 times 7a plus 3 to the k. This is divisible by 4. For question 3, we prove that n cubed minus n is divisible by 6. The base case for n equals 1 gives 0, which is divisible by 6. We assume k cubed minus k equals 6a. Then we consider k plus 1 cubed minus k plus 1. Expanding this gives k cubed plus 3k squared plus 3k plus 1 minus k minus 1, which simplifies to k cubed minus k plus 3k squared plus 3k. Substituting 6a for k cubed minus k, we get 6a plus 3k times k plus 1. Since k times k plus 1 is always even, we can write it as 2c. So we have 6a plus 3 times 2c, which is 6a plus 6c, or 6 times a plus c. This is divisible by 6. For question 4, we prove that 3 to the 2, n plus 2, minus 8n minus 9 is divisible by 64. The base case for n equals 1 gives 3 to the 4 minus 8 minus 9, which is 81 minus 17, or 64. This is divisible by 64. We assume 3 to the 2, k plus 2 minus 8k minus 9 equals 64a. Then we consider the expression for k plus 1. We rewrite 3 to the 2k plus 4 as 9 times 3 to the 2k plus 2. Substituting 3 to the 2k plus 2 equals 64a plus 8k plus 9, we get 9 times 64a plus 8k plus 9 minus 8k minus 17. This simplifies to 9 times 64a plus 72k plus 81 minus 8k minus 17, which is 9 times 64a plus 64k plus 64. Factoring out 64 gives 64 times 9a plus k plus 1. This is divisible by 64. Finally, for question 5, we prove the inequality 2 to the n is greater than n squared for n greater than or equal to 5. The base case for n equals 5 gives 32 is greater than 25, which is true. We assume 2 to the k is greater than k squared. Then 2 to the k plus 1 is greater than 2k squared. We need to show that 2k squared is greater than k plus 1 squared, which is k squared plus 2k plus 1. This simplifies to showing that k squared minus 2k minus 1 is greater than 0. The roots of k squared minus 2k minus 1 are 1 plus or minus the square root of 2. The parabola opens upwards, so it's positive for k greater than 1 plus the square root of 2, which is approximately 2.414. Since our base case is n equals 5, k is greater than or equal to 5, so the inequality holds. Therefore, 2 to the k plus 1 is greater than k plus 1 squared. That concludes our session on mathematical induction for divisibility and inequalities. I hope this video has provided you with a clear and rigorous understanding of these important concepts. Remember to practice these techniques regularly to build your confidence and problem-solving skills. Thank you for watching.